Good afternoon to all. Today we are going to discuss about nucleophilic substitution reactions. I have already discussed about SN2 reaction in the morning class. Anyway, I will be repeating that once again. Okay. Nucleophilic substitution reactions. So, from the word we can understand that from this nucleophilic substitution we can understand that a nucleophile will get substituted. Since a nucleophile is getting substituted, these reactions are generally known as nucleophilic substitution reactions. So, here when we consider an alkyl halide, for example, CH3, CH2, Cl. This is an alkyl halide. This is nothing but ethyl chloride. Now, if you see, there is electronegativity difference between carbon and halogen. Halogen is more electronegative when compared with carbon. So, chlorine, if you see, it will get partial negative character. Carbon, it will get partial positive character. So, since carbon is having partial positive charge, these will be attacked by the nucleophile. When nucleophile attacks this carbon, the chlorine, nothing but the halogen which is present here, it will get removed. Nothing but in place of this chlorine, nucleophile will get substituted. That is why these reactions are known as nucleophilic substitution reactions. Nucleophilic substitution reactions, they are classified into two types. Okay, they are nothing but SN1 and SN2. First, we will be discussing about SN2 and then we will be discussing about SN1. Okay. Let us see. SN2. SN2 is nothing but substitution nucleophilic bimolecular reaction. Substitution nucleophilic bimolecular reaction. Let us consider an example to understand this SN2 reaction. Okay. Chloromethane. Okay, so this is the alkyl halide which I am considering, and it is treated with a nucleophile. Let us consider this as OH minus. So this OH minus can be from potassium hydroxide. Potassium hydroxide, if it undergoes dissociation, it forms K plus and OH minus. OH minus ions which got produced, they will act as nucleophiles. Nothing but when we are treating alkyl halide with potassium hydroxide, hydroxy ion from the potassium hydroxide, it will react with this methyl chloride. Let us see how it reacts. So here if you see this OH minus ion, it will attack this carbon. Why it is attacking this carbon? Because the carbon is partially positively charged. Okay, chlorine is partially negatively charged. Due to the difference in electronegativity, partial positive charge gets developed on carbon, partial negative charge gets developed on chlorine. Now, if you see this hydroxy ion, nothing but it is a nucleophile, it will attack this carbon from the back side. In this way, it will not attack the carbon from the front side. Why it won't attack the carbon from the front side? The reason is nothing but chlorine is present. Chlorine is also a nucleophile. So, there will be a repulsion between this hydroxy ion as well as the chlorine present on the carbon. That is why this nucleophile, OH minus ion, it cannot attack the carbon from the front side. So, it will try to attack from the back side. So, if it attacks from the back side, okay, this is how the intermediate, nothing but the product gets produced. as soon as the OH gets attached to the carbon, the bond between the carbon and this chlorine, it will start weakening, and a new bond between the carbon and the hydroxy group, it will start forming in this way. This is nothing but the transition state. This is nothing but the transition state. In this transition state, if you observe, carbon is bonding with 5 groups. Okay, carbon can form only 4 bonds, but in this transition state, it is linked to 5 groups. So it will be unstable in nature. So since it is unstable, it will kick out this chlorine, halogen, and it forms the product as in this way. Nothing but methanol and halide ion gets produced in this way. Okay. So here if you see the structure of the product and the structure of the reactant. Okay. The structure of the product, nothing but methanol, it has inversion in configuration. There is inversion in configuration when we observe the product than when we compare it with the reactant. Okay. This is one thing. So this is about substitution nucleophilic bimolecular reaction. In this reaction there will not be any intermediate. Keep that in mind. In this reaction there is no intermediate. Only transition state is present. Okay. See, this transition state, it is highly unstable in nature. Why it is unstable? Because carbon is forming 5 bonds here. If it is forming 5 bonds, it will be unstable. Carbon can form only 4 bonds. In the transition state, it is forming 5 bonds. It will be unstable. That is why it immediately gets converted into the product in this way. Okay. And if you see this reaction, it takes place in a single step only. SN2 reaction takes place in a single step. The next thing is nothing but regarding the rate of this reaction. The rate of this reaction, it depends both on the concentration of reactant as well as the halogen. On both the things, the rate of reaction will depend. That is why we are calling it as a bimolecular reaction. Rate of reaction depends both on the alkyl halide as well as the nucleophile. Nothing but on both the reactants, the rate of reaction will depend. That is why it is a bimolecular reaction. Remember these points. So what you want to remember is nothing but SN2, it takes place in a single step. It takes place in a single step, and rate of reaction depends on both the reactants. On both the reactants. Both the reactants means one will be alkyl halide, the second will be nucleophile. Okay. So the next thing is nothing but when we consider primary alkyl halide, secondary alkyl halide and tertiary alkyl halide. Among these three, which is more reactive towards SN2 reaction? So primary alkyl halide will be more reactive towards SN2 reaction. The reason is nothing but in this steric hindrance will be less. Since steric hindrance is less, primary alkyl halides will be more reactive towards SN2 reaction. Let us see that in a detailed way. how primary alkyl halides are more reactive towards SN2 reaction. Let us see that. Let us take an example to understand this. Okay. This is nothing but methyl chloride, chloromethane. Now if you see, when one of the hydrogen from this chloromethane, if it is getting substituted by CH3 group, if this hydrogen, if it is getting substituted by this methyl group, then it will form chloroethane in that way. Here if you see, if SN2 reaction wants to take place, then the nucleophile, it wants to attack the carbon from the backside. When it wants to attack the carbon from the backside, hindrance should not be there. For the nucleophile to attack this carbon, hindrance should not be there. Okay. Here if you see, hydrogen is small in size when compared with methyl group. Okay. So when all the three groups of the carbon, if they are hydrogens, it will be easy for the nucleophile. What is the nucleophile in our reaction? OH minus. So it will be easy for this nucleophile to attack the carbon, because they will give space for the OH minus ion to attack on the carbon, since they are small in size. Whenever these hydrogens are getting substituted by the bulky substituents, nothing but like methyl groups, then these bulky substituents, they will not give space for the nucleophile to attack the carbon. If they are not giving space for the nucleophile to attack the carbon, then SN2 reaction will not take place. Okay. When compared with these, okay, methyl chloride will be more reactive towards SN2 reaction. In the same way, when the second hydrogen is also getting substituted by the methyl group, in this way, then steric hindrance will be more. When compared with this, in this steric hindrance will be more, because two bulky substituents, they will occupy more space. If they occupy more space around the carbon, then the hydroxy group, nothing but the nucleophile, find more difficulty to attack the carbon from the backside. So the reactivity further decreases in this. Let us see that the third hydrogen is also getting substituted by the methyl. If the third hydrogen is also getting substituted by the methyl group in this way, then the nucleophile, it will feel more difficulty to attack the carbon, because these three bulky groups, they will not give space for this nucleophile to attack the carbon. So the reaction will be further slow. Here if you see, this is a primary alkyl halide, this is a secondary alkyl halide, this is a tertiary alkyl halide. Okay. So if you see these things, the rate of reaction will be primary greater than, secondary greater than, tertiary. The reason is nothing but steric hindrance. As we move from primary to tertiary here, okay, steric hindrance is increasing, because since the methyl groups are getting increased, okay, so the hindrance provided by them for the attack of this nucleophile on the carbon will also increase. Nothing but these bulky substituents, they will not allow the nucleophile to attack. They will occupy all the space present around the carbon. They will not allow this nucleophile to attack. If this is not attacking the carbon, substitution will not take place. SN2 reaction will not take place. Okay. Primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. Here you can consider methyl chloride. Methyl chloride will be more reactive. So this is the order. So this is something about SN2 reaction. And since the product has inversion in configuration when compared with the reactant, we also call these SN2 as Walden inversion. Okay, inversion in configuration will take place when compared with the reactant in the product. So that inversion we call it as Walden inversion. So these are the things about SN2 reaction. Now let us discuss about SN1 reaction. SN1 reaction. SN1. So if you see the full form, it is nothing but substitution nucleophilic unimolecular reaction. Unimolecular reaction. Substitution nucleophilic unimolecular reaction. Okay, nothing but in this case, rate of reaction depends only on one reactant. The rate of reaction depends only on one reactant. Only on one reactant it depends. Okay. So that is why we are calling it as unimolecular reaction. And this SN2 reaction, it takes place in two steps. SN2 reaction, it takes place in two steps. It takes place in two steps. Okay. Let us take an example to understand this. Let us take an example to understand this. Okay. So this is nothing but tertiary butyl bromide. Tertiary butyl bromide. Okay. Tertiary butyl bromide. These on reaction with a nucleophile. Let us consider OH minus. This is a nucleophile. Okay. Then it will form the product as tertiary butyl alcohol will get produced in this way. Along with that, okay, Br minus gets removed in this way. Okay, let us see the mechanism. So here, if you see step 1, initially carbocation will get produced from this tertiary butyl bromide. Okay, nothing but the halogen which is present here, it will get removed. See the first step. This is nothing but tertiary butyl bromide. From this, if you see halogen, it gets removed. When halogen gets removed, the carbocation which gets produced is nothing but this one. This is tertiary butyl carbocation gets produced. This carbon got attached to 3 other carbons. Okay, that is why this carbocation is known as tertiary carbocation. So this is the first step. Nothing but formation of carbocation is the first step, and this is the rate determining step. Formation of carbocation is the rate determining step. Nothing but step 1 decides the rate of this reaction. Okay, as soon as this carbocation gets produced, now the nucleophile will attack it. In step 2, if you see, so this carbocation it will get attacked by the nucleophile. Okay, and it forms tertiary butyl alcohol. Here if you see this nucleophile, it can attack this carbon either from the front side or from the back side. From any side, okay, nucleophile can attack this carbon having the positive charge. But in case of SN2, nucleophile will attack the carbon only from the back side. I have already said the reason why the nucleophile attacks the carbon only from the back side, why not from the front side. Okay. In case of SN1, okay, after forming the carbocation, okay, hydroxy group, here nothing but nucleophile. It can attack this carbocation either from the front side or from the back side, leading to the formation of product release. So formation of this carbocation is the rate determining step. So this is about SN1 reaction. In case of SN1 reaction, rate of reactivity, it depends on the stability of carbocation. When we consider different carbocations like primary carbocation, for example, primary alkyl halide let us consider, secondary alkyl halide, tertiary alkyl halide. Among these three alkyl halides, okay, the carbocation formed from tertiary, it will be more stable. That you already know, because since there are three alkyl groups present here, they can donate the electrons to the carbon having the positive charge. Nothing but the positive charge gets nullified. Okay, so this is primary alkyl halide, secondary alkyl halide, tertiary alkyl halide, which is more reactive towards SN1 reaction, means it is tertiary alkyl halide. So tertiary is greater than, secondary is greater than primary. So why this is the order? The reason is nothing but stability of carbocation. The carbocation formed from tertiary alkyl halide is more stable than secondary alkyl halide, than primary alkyl halide. That is the reason. Okay. And generally, this SN1 reaction, it takes place in polar protic solvents. Remember this point. Polar protic solvents. Okay. So SN1 reaction, it takes place in polar protic solvents. Okay. So this is about SN1 reaction.